Today we have Professor Micheal Petterson from the Auckland University of Technology to talk to us on the topic hazard and risk from geological deep time and Anthropocene perspective. It's our great pleasure to have you, sir. Thank you very much for accepting the invitation. Professor Deepthi Wickramasinghe's research group, Environment and Resilience Pitch, is hosting today's event. And while thanking Professor Deepthi Wickramasinghe's research group, let me invite Professor Deepthi to introduce the speaker. Over to you, madam.
Thank you, Sachini. Good afternoon, everybody, and good evening to our guests from New Zealand. And it's my pleasure to welcome very warmly Professor Micheal Petterson, who's one of Damithi's PhD supervisors. And thank you very much, Mike, for accepting our invitation. And now I would like to invite Deepthi to speak a few words about Mike. Thank you, Deepthi. Over to you.
Thank you, madam. Don't just think about yourself and your own career. Be passionate, be persevering. Use your research for excellent blue skies work, but think about how you can use it for the benefit to the planet, its people, and the students around you, says Professor Micheal Petterson. Professor Micheal Petterson is a professor in environmental science at Auckland University of Technology, Auckland, New Zealand. His expertise has acquired in geology, geological mapping, geotectonics, geoscience and development, international development, leadership in geoscience organization, environmental geoscience, economic geology and society. His teaching areas include our dynamic earth, geology, landscape and environment, structural geology and tectonics, sedimentary geoscience and volcanology. A notable contribution during his career has been the instrumental role he has played in negotiating elements of a new 50 million US project with the World Bank to help establish and implement a disaster resilient program in the Pacific Islands region. Countries involved in the project included Samoa, Tonga, the Marshalllands, and Vanuatu. But according to him, his most challenging career experience today was the designing and implementing a 5 years program of strengthening geological institutions in Kabul, Afghanistan during the period that followed the Taliban exit from government is his most challenging part of his career. He says his biggest eureka moment was the shocking realization that so many millions in the world live with war, famine, degrading poverty and fear. Therefore, he sees challenging ideas and thinking creatively to benefit humanity as a core part of his role as a scientist. At the same time, he is my co-supervisor, one of the most beautiful human beings I've met. And I'm so happy my my bachelor's studies, that means my bachelor's department, my professors, lecturers, and doctors who took me to my bachelor's level are meeting with my now supervisor, Micheal Petterson. It's over to you, Mike.
So, bohom yeshtuti, Sachini, Saha Deepthi, Saha Demitri. Thank you so much for that. Ayu Bawan. Kohamada? Lastida? Lastida, Mama Patanganang Mage lecture done. Okay, I will give my lecture now. So first of all, I'm very honored to be asked to come here. Thank you, Demitri, for asking me, and thank you for all of you for agreeing for me to speak with you. It's a great honor to talk with you and share some thoughts, excuse me, on our planet. And I also know it's wonderful to speak to the oldest university in Sri Lanka. You've got a long history dating back to June 1870 as a medical college. And then in 1906, you were given a university status as the University of Ceylon and now University of Colombo. So great honor to talk to you. So because I know that some of you are interested in risk to life, risk to ecosystems and things like this, I'm trying to give a talk here which gives a planetary perspective from a geologist's lens, but it's not going to be traditional geology as you may think about it. I'm going to try and weave together a story looking at the whole Earth and following certain trends in the Earth and what this can tell us about risks today and tomorrow. So this is planetary trends and risks, I've called it. So I'm going to talk a little bit about energy and heat because I'm going to track at least part of the talk, greater part of this talk, through the idea of energy and heat. We're going to learn some lessons from deep time and plate tectonics. We're then going to move to the surface of the Earth and we're going to look at heat with respect to hydrometeorological systems. We're then going to look at the human factor on Earth. So that's much more recently. We're going to look at something called the Anthropocene. And then we're going to try and put all this together and say, well, you know, so what, in a sense, what can we learn for risk management and for biodiversity on Earth and for life on Earth in general, and looking for the future for planetary management and planetary health. So energy and heat is one of the connecting themes. And that man at the top there, that very famous man, Einstein, he was the one that showed us the equivalence, for example, between energy and mass with this famous equation, E equals mc squared. And what that's basically telling us is that if we look at the universe, things will alternate between energy and mass. And we see this in our universe. So at the very beginning of the universe, at the Big Bang, all we really had was energy. And of course, now we have this incredibly rich, very diverse, very heterogeneous universe with planets and stars and galaxies and all of this sort of stuff. And it went from one to the other, okay, over a very long time period from our human perspective. But in essence, it changed from being very energy dominant to a situation today where it's part energy and it's part matter, like suns and stars and things like that. And one of the definitions of the death of the universe actually is where everything is the same temperature. Just imagine that. Imagine that on our Earth too. If everything was the same temperature, would anything actually happen? Would there be movement of energy anymore? Because as we often can observe, it's the movement of heat on our Earth that makes things happen. And I'm going to be taking that theme up for a little while. So I'm going to look at the deep Earth, look at the energy movements in the deep Earth, then move to the atmosphere. One of the advantages we have as a geologist is we have time. Now in the universe, we have 13 billion years or thereabouts. Earth, we have a little bit less, but still an awful long time compared to our human sort of idea of time. So we have in fact 4.56 billion years of evidence. But we have to know how to read the evidence, just like we can't read books if we don't know our symbols and our alphabets and our different scripts around the world. If we look at deep time, what can the Earth tell us about planetary boundaries? Because much of what we talk today in climate change, for example, or whatever you want to call it, climate crisis or whatever, we're often asking the question, well, what are the limits of X? What are the limits of Y? If we do this to one part of the Earth, what happens to another part of the Earth? So let's see if we can learn something from this sort of analysis, from looking at deep time. Can we actually learn something from that? So I'm going to look at the extremes of Earth and see what they can tell us about how the Earth functions as a planet. So one thing we know is at different times in past and geological time, we've had what you call ice house Earth. We've had an Earth dominated by colder temperatures and a lot of ice at the surface of the Earth. In fact, there was one period a long time ago, but we know if it happens once, there's no reason why it can't happen again. It's called the cryogenic period. As you know, cryo means ice. This is a period about 720 to 635 million years ago. We think that the whole of the Earth was covered in ice at this point. So this was a very cold Earth. And we've had at least 5 or 6 different ice ages, not as extensive as that one that we know about, that have occurred at different times on the Earth. In fact, we're actually in an ice age today, although, of course, the talk isn't about ice age, it's all about global warming and everything. But if we forget about the anthropogenic thing for a moment, we're actually in what's called an interstadial, in a warm period in an ice age, which has lasted about 30 million years on Earth. And we're still in that period. However, humans are becoming such a planetary changer that maybe we're going to move out of the ice age quicker than we would have done naturally. So that's one thing the Earth tells us about the colder times. We also know, however, there's been much greater periods of warmer times on Earth. And this graph on the right there is on the bottom. If you look at the bottom, that's in millions of years. You've got today on the right, and we've got 500 million years ago. So this is only 1/9 of geological time we're seeing here. The previous 8/9 we could do something similar, but the data gets a lot more vague. The more you go back in time, then the mistier everything becomes, the foggier everything becomes. For what this graph tells us is that for the bulk of the time in the last 500 million years, the Earth has actually been pretty warm. It's been quite a lot warmer than the present day, in fact. And we've had a much hotter periods and quite long periods of hot periods, if you see that in red at the bottom of that slide, from about 500 to 360 million, 250 to 200 million, 170 to 40 million years. So in fact, the Earth is used, as a planet, I mean, the Earth is used to being a lot warmer than it is now. So the last 2 slides, and the last one shows us that we can get much colder than today, and we can get significantly warmer than today, even warmer than the scenarios that are being postulated for planetary change at the moment, anthropogenic climate change. If we look a little bit more closely at this, and so I've blown up and used a slightly different scale to the one before. This documents the temperature of the Earth. These are average temperatures of the Earth as a planet. And if you look at the arrows on the bottom there, this is not a linear scale at the bottom. We're amplifying the more recent times because as humans, of course, we're more interested in the recent times with the climate change debate. But the red zone is from 500 to 100 million years ago. The orange zone is from about 100 million years ago to 1 million years ago, and the blue is the last 1 million years. So this is not a linear scale. So if you can please just get your head around that, I'm sure you can. If we look at first at the red zone, again, we'll see that for the bulk of that red zone, we were significantly hotter than today. 0 is the temperature of today. Okay, so the average temperature of the planet today is 16 degrees C. Of course, in Sri Lanka, you won't think that because your average temperature is more like in the high 20s. But here actually in Auckland, probably 16 degrees C, well, probably a bit less than that is our average, but it's not far off that. That might not seem very high, but if you compare that with Mars, for example, which is minus 80 degrees C, and Venus, which is hell-like 400 degrees C at the surface, then we have a much more equitable temperature for life as we know it, at least. And again, we can learn, well, when we're thinking about planetary boundaries or planetary limits, what do we learn from deep time in Earth? Well, we know that Earth has bobbed around between plus 30 degrees C. So the hottest you get to about 33, 34 degrees in Sri Lanka, don't you? So on your hot day, that could be the average global temperature in the hot periods on Earth. And then the coldest is about minus 10. So that would be probably down getting towards the Arctic and the Antarctic, the average temperature of minus 10. But that's quite remarkable. That's not a huge temperature difference in terms of variations in the average temperature of a whole planet. When you look at something like the Mars or the Moon, for example, which can go from about plus 100 to minus 150, even from day to nighttime on the Moon. Our planet has got this remarkable control on temperature, and that's one thing we can learn from looking at deep time and looking at proxies for temperature. Another thing to note, I think this graph brings out very well, is that from about 50 million years ago, the Earth has been cooling. You can see from the green, the black, and then into the blue. It's been cooling, and then we're in the interstadial now on that period called the Holocene. And of course, we're now adding to that with our human impacts. The reason the Earth cooled at that point after a very long warm period before then is because the Himalayas started to form. So believe it or not, when we build mountains, for example, that actually has the ability to cool the Earth. Why? Because when we grow mountains, we are pushing the crust up into the upper atmosphere. We erode a lot more material, a lot more rock, we oxidize it, and we can lock up carbon along with the along with all of those erosional processes. And that's one way of cooling the planet. Then we can look at sea levels. We're talking at the moment, if you look at the IPCC latest predictions, we're talking about maybe of 1 meter or more at 2100 rise in sea level. And we get quite concerned about that. And so we should be, as many of us live close to sea level. However, 1 meter is nothing compared to the fluctuations that the Earth is seeing in terms of sea level rises. Times in the past, we've had the sea level at 400 meters higher than the present. And in the last big ice age, it fell to about 120 meters lower than the planet. So at that time, for example, Sri Lanka would have been part of the Indian subcontinent. You wouldn't have had the ocean between you and India, which I think you quite like at the moment, don't you? But back in those days, you wouldn't have had that. You would have been joined by land between Sri Lanka and India. And similarly here in New Zealand, we're 2 islands now, but back in those days, it would have been just one land mass. And we would have had significantly more land than now. But actually, for the great bulk of geological time, we've had a lot less land than we have now. That means a lot less land above seawater than we have now. And of course, that has huge implications for terrestrial ecosystems and marine ecosystems. So a lot of the Earth might have looked like this. Of course, we know continents move and they move around the Earth, and what we see as a continental distribution of today is just one snapshot in time. And this is from a period called the Silurian period, but I could have picked any period for different, it looks quite different when we go that far back in time. And we can see we still have continents, and plenty of them, probably a little bit less, but similar sort of area of continents to today. But the big difference was about half of those continents were actually drowned in shallow seas. And we would have had, and this was because sea levels were a lot higher. And there's lots of controls on sea level that I haven't really got enough time to go into in this lecture, but we can talk about it later if you want. But suffice to say that, again, we're living in quite a lucky time from a terrestrial animal point of view, like ourselves, because we've got a lot more land above sea level than normal on this Earth of ours. And then another thing we can do is we can look at life, and we look at the patterns of life in deep time. Because one question we're asking now is, well, what are we doing to biodiversity on the planet? And it's not good news, is it? As we'll talk about a bit later. So as I know many of you are in the biology side of things, you'll know far more about this than I do. But if you look back in time on Earth, then for 8/9 of the period of the Earth's existence, we did not have complex life. So when we look back that far back in time, older than about 540 million years ago, we don't really know if there were any extinction periods because we didn't have great diversity of life. What we do know, however, was that whatever the Earth threw at life survived, even in those early life conditions. So life arrived on Earth about 4 billion years ago, but it was very simple, like cyanobacteria and prokaryotes, eukaryotes, and things like that for a long, long time, until about 700 million years ago when complexity kicked in. And then we really started to get complexity from 540 million years ago. So in this 1/9 of time that we know about, there have been 5 mass extinctions, and they're marked here at the end of the Ordovician, the end of the Devonian, the end Permian, which was the biggest one, the end Triassic, and the end Cretaceous. And these were all caused by different events, some of them being climate related, some of them being geological related, some of them being astronomical related in terms of a big meteorite impacting on the Earth and things like this. So There's lots of debates about why we had these periods, but whatever the debate and whatever we can come up with, what we do know is that the Earth system was stressed to the point where life struggled. That's the bad news, but the good news is it always survived. The end Permian one, for example, apparently killed out, or some people would argue that it killed something like 90% of terrestrial life. And yet life survives. And also what happens in these periods is you get punctuated evolution, you get rapid evolution, and you tend to get a jump to more sophisticated life forms. The classic one being at the end of the Cretaceous, where that tended to wipe the reptiles out, for example, or the dinosaurs, the famous ones and things like that, the megafauna reptiles. And it allowed the mammals to flourish, which eventually led to the evolution of ourselves. So there's good and bad to these extinctions, actually, when you look at them. But the message I want to take from it is that whatever we throw at the Earth as a human, I think life will survive. We might not, and certain species might not, but life in general, at least geology teaches us, should survive. So what are the conclusions when we look at deep time? Temperatures haven't varied hugely for when we think about planets and the variations you can get in planets. Most of the time that we know about, that we've looked at, Earth has been significantly warmer than today, and life has developed and even flourished in those times. Earth has experienced a lot of ice ages. In fact, quite recently, we had something called the Little Ice Age, which was from the 14th to the 19th century, which was a significantly colder period than what we experience today, and from the middle of the 19th century. Earth has had many hothouse periods. Sea levels have been a lot higher and a lot lower than today. We've had mass extinctions. So in geological terms, if we're thinking about climate change today, you know, the good news is the Earth's going to survive. The Earth will manage all of this in its own sweet way. It has got time on its side. It's got a lot of processes on its side. And I think life will also survive. That's what it's telling us, whatever we throw at our planetary system. So now let's look at heat within the Earth and how that's driven a lot of this and how this has helped produce a stable Earth. And if we look at internal heat production in the Earth, it's largely produced, it's largely produced by radioactive isotopes, things like uranium, thorium, potassium, cesium, things like this, which are present in the Earth in great quantities. And some of these have very long half-lives of billions of years and things like that. So they can produce heat for a long time. Having said that, they still decay exponentially, as you know, as radioactivity. That's the nature of radioactivity. And today we've got about 1/3 of the total heat production in our planet than we had when Earth first formed. However, it's still enough for us to have a very dynamic tectonic Earth. And that's important for us because we're learning more and more that that to get a planet which is well regulated and produces ecosystems which last long enough for life to evolve and develop, you pretty much need some sort of tectonics which regulates things from the internal workings of the planet to the external workings of the planet and beyond even. This isn't the case, for example, for the moon. The moon is a classic one. It's a dead planet, never had life, and didn't evolve very much geologically. And the reason was it didn't have much internal heat. So it never had the tectonics that we have. It never had an atmosphere and things like that. So it's not a good place to look for life at all. Not life as we know it anyway. You never know, we might get surprised in the future, but from everything we know, it's a dead planet. Mars, we're looking desperately for life on Mars, but even if we find it, we're not expecting to find sophisticated life. It's probably going to be fairly primitive bacterial type of life. We also think that early Mars was probably very similar to early Earth, but the difference was it ran out of steam, literally. It didn't have the internal heat that Earth has. And this led to a whole number of things that, again, I haven't really got time to talk about now, but culminated in things like the loss of the atmosphere and the loss of surface water and things like this, which made it a lot more difficult for life to evolve beyond a certain point and for a great variety of ecosystems to develop like we see on Earth. So there's a big link, what I'm arguing here, there's a big link between internal heat, tectonics, active tectonics, and the regulation of ecosystems on the surface of the Earth. So this is what we see in our Earth, and it isn't just in our Earth. Venus, perhaps, for example, has something a little bit like this, but for different reasons, Venus evolved in different ways to us, and even their tectonics couldn't regulate ecosystems like ours. What we get then is a heat transfer from the hot middle part of the Earth. So the middle of the Earth is about the same temperature as the surface of our sun, about 6,000 degrees C. And another amazing thing is that our mantle, where you see all those convection cells, our mantle over a long period of time can convect. It's got this amazing quality of, in a short period of time, it will snap, or much of it will snap, just like a brick or something at the surface of the Earth. But over a long time, it will flow. And this flowage of the material over a long period of time allows for convection. And this drives our tectonics. So it's driven by heat, and it will die. This tectonics will die when the heat dies. And as we know, we've got a whole series of plates on Earth, and around about there's a very close link between this active planetary system and planetary life. And if we look at all Earth systems, whether it's atmosphere, biosphere, hydrosphere, lithosphere, geosphere, all these sorts of spheres, we're now learning more and more, and the connections and the interconnections and the feedback mechanisms between one and the other. And if you impact on one system, you will impact on the other. So luckily for us, we have this dynamic tectonics, which helps stabilize the other Earth systems that we can see. And they do this by very dynamic interactions. And again, I don't want to dwell too much on the sort of geology of the interactions, but in simple terms, they pull plates apart, they push them together, they melt them, they split them, they create new ones, they destroy old ones. And these are the things that create our major tectonic activity, which we see largely in phenomena such as earthquakes and volcanoes and things like that. So for example, the volcanic processes are the very processes that produced our atmosphere. Now, our first atmosphere was a solar atmosphere. That was quickly replaced by a degassing atmosphere from the interior of the Earth through volcanism. And volcanism still very strongly controls the nature of our atmosphere. And we get this cycle of tectonics, which a man called Wilson, a researcher called Wilson, was the first to put together in the late 70s, early 80s. And we can observe basically the birth and death of oceans. So unlike continents, our oceans are young. The youngest parts of our oceans are only about 200 million years old, whereas the oldest parts of our continents are over 4 billion years old. There's a big difference in the big nature and the character of oceans and continents. So to create our oceans, we split our continent apart. The early stage, we get something like the Red Sea, for example. That's not a sea, that's an ocean. We spread that a bit further and we get our Atlantic, something like the Atlantic. We then can grow a huge ocean like the size of the Pacific, but the Pacific is getting smaller on all sides. And then we can close our oceans somewhere like the Mediterranean Sea, for example, still has some relics of ancient ocean in it. And then finally we will collide just like we get in the Himalaya. And then the whole cycle keeps going and going and going, as long as we have the heat energy to drive the system. And it's this constant interaction which regulates all the other Earth systems. So we should be, although we probably never think about this, we should be quite grateful to tectonics, because without it, we wouldn't have the Earth we have now in terms of life and diversity of life and a stable Earth. And one place we can see this very clearly is where I'm speaking to you from in New Zealand. So New Zealand is part of a continent called Zealandia, which you may or may not have heard of. It was only first proposed in the early 2000s, actually. That was when we discovered that area outlined in the diagram here was actually not ocean, it was continental material. And only 2 bits of land within only 2 bits of this continent are actually above sea level. and that is New Zealand itself and New Caledonia. And the only reason it's above sea level is because of active tectonics. New Zealand is the meeting ground of the Pacific plate and the Australian Indian plate. And the interaction between those two push this Zealandia, compress it and push it and do all sorts of things to it and raise it upwards. Similarly, New Caledonia is another one. So around about 90% or over 80% anyway of this continent is beneath sea level, just because the natural buoyancy of this continent for a whole bunch of reasons is such that it's below sea level. So it's a nice illustration that, you know, sometimes we might get caught up in looking at the bad sides of volcanoes and earthquakes and things like this and the potential hazards they produce. But without them, you know, many of us wouldn't even have land, and that's not very good for an animal like us, which needs to live above water until we develop an ability to breathe under the water. So this is a diagram of the plate boundaries, and it's at the plate boundaries or where we get 90% of our earthquakes and our volcanoes, and these are where we produce some of the hazards which present us with risk that we have to manage, and we have to place ourselves in a position of safety around these sorts of geological hazards. The biggest risks are big earthquakes and shallow earthquakes. So earthquakes that are about 10 kilometers or less are big. These are the ones that tend to produce impacts which humans worry about. So plate tectonics produces these types of earthquakes. It also produces tsunamis, which you in Sri Lanka know only too much about, unfortunately. And we can look at different regions of the world, and we can start using our geological information to manage planetary risk. So we can actually map where the greatest risks are for earthquakes, from volcanoes, from tsunamis. We're only really learning about tsunamis since that terrible 2004 tsunami. Before then, only really the Japanese took it that seriously and knew a lot about it for obvious reasons, because, well, it's a Japanese name, isn't it? Because they get so many of them. Anyway, the point is that because of our new understanding of geology and planetary functions and plate tectonics and things like that, we can start to quantify and spatially map where risk is and the causes of risk. And we can start to statistically analyze, if not predict exactly. We were not in a position, for example, where we can predict a volcanic eruption will occur in country X on next Tuesday, or an earthquake of magnitude 7 will occur in North India next Thursday. We may never get to that point, but we can get very much got to the point where we can identify various levels of risk and statistically suggest when we might get the next big one. So this was the big, here's an example of the sorts of things we can do now to help us manage risk and understand risk better from a geohazard point of view. This was that huge Great East Japanese earthquake, the Fukushima earthquake of 2011, which emanated just east of the northern eastern part of Honshu, the big island in Japan. And what is remarkable about this diagram that you can see is how this earthquake moved right across the Pacific Ocean and the tracks it produced. And also, I think what is also remarkable about this is how we can use the data, and we can track the movement of these tsunamis so well. And now in the Pacific, since in fact the Boxing Day, the 2004 December 26th tsunami, we have a bunch of ocean buoys which are specially designed for detecting tsunami waves, which travel at the same speed as a jet airliner, about 500 miles an hour or 800 kilometers an hour across the ocean. And I'm speaking to you in Sri Lanka that only knows too well about this particular one, which killed over 200,000 people, 30,000 of them your fellow citizens in Sri Lanka, unfortunately, and also on the eastern and southern side of India. The worst one was in Aceh, in the worst casualties were in Aceh in Sumatra. And that was from a big fault movement in across the Andaman Fault in the Andaman Sea. You can see where the dark brown is. And again, we can map and track what happened to this earthquake. It even killed people on the eastern side of Africa. A few casualties were there, which is amazing. But we can now track these things. And what it also tells us And actually, this is an example. Usually we go to deep time, we find things that have happened in deep time and we apply it to today. But that can happen the other way around. And this is an example where it's happened. Since the 2004 tsunami, geologists all over the world have been mapping tsunami deposits. And they've been learning an awful lot about that in terms of historical, geologically historical tsunamis and things. This is a very good example then of internal heat manifesting itself as tectonics, which then manifests itself as plate movement and fault movement. And in the case of the tsunami, then transfers that energy into the ocean, which then produces a big, in this case, incredibly destructive wave. And the more we know about this, the more we can plan and mitigate these sorts of disasters or potential disasters. So what do we learn from tectonics and heat there and life and risk? So the good thing is planetary tectonics regulate planetary systems. Even, for example, the fact that we have a liquid core and we have an Earth that rotates produces a magnetic field, which we now think is key for developing life on Earth because it protects us from radiation, for example. Mars doesn't have one. And that's another reason why it's more difficult for life to develop there. And this impacts so many things like the shape and size of continents, the shape and size of oceans, the interactions between the various systems, and the production of the geohazards, and our scientific understanding of that and how we can use that to manage risk in the world. We know that we have significant heat in the Earth still. It's a lot less than the earlier Earth, but sufficient to drive sophisticated tectonics. And when we compare and contrast with other planets, which is what we do as geologists now, we're not just stuck to our Earth anymore. We can see, we can look at the spectrum of planets and planetary evolutions. Plate interactions look like they're very important for ecosystems for life. Some sort of tectonics, it doesn't have to be exactly like we see on Earth, but some sort of tectonics is helpful, if not fundamental, for setting the scene for life. But they do produce geohazards. We need to know about them. We need to know how they are produced and how they occur and what their impacts are. And our knowledge of these hazards has grown by orders of magnitude, particularly, I would say, since the 1950s and things like that, with the better instrumentation, with the way we can analyze big data sets and things like that. So now let's move from the deeper Earth to the planetary surface. Let's look at hydrometeorological systems. And I'm still going to follow a similar tack here because we're still following heat and energy. It's heat which is driving the system. So in the case of the surface of the Earth, where do we get our heat from? Well, of course, the bulk of it will come from the sun and solar radiation. And then again, just think how lucky we are. We've got a star which is very stable. Many stars are not. Many stars vary and they can pump out radiation, like variable stars. They can pump out radiation that's 10 times more one week than another week. Well, if we lived around a star like that, it's very unlikely we could have life on Earth. So thank you again we should be very grateful to our star, which has been going 4.6 billion years, hopefully another 6 billion years of life, we think, before it will expand and swallow us up along with Mars when it gets to its red star stage. But in the meantime, it's an incredibly consistent sun. That doesn't mean it doesn't vary. We know from the past it has varied, but it's the main giver of radiation and heat on the Earth. Internal heat too, and then it all gets distributed in the ocean and in the land and in various parts of our hydrological and meteorological system on Earth, and we can track it through the water cycle and things like that. So if we look at, I'm going to dwell a little bit now into humans and what humans do. But at the moment, as we said before, we've got an average global temperature of 16 degrees C, but we know that in previous times, it's gone up to 30 degrees C. And we think we're probably not going to be able to keep our Earth. I know they're talking about 1.5 degrees C, but I don't know if you heard the news today. There's still lots of greenhouse gases getting pumped out there. I think we're going to really struggle personally to keep it to 1.5. So I think we've got a plan for 2 degrees C. I do think that in the end, you know, we're going to decarbonize and all of that, but it's just going to take time. With the best will in the world, managing people is not easy, as we all know. So if we add another 2 degrees to the system, we're actually allowing the clouds, for example, to hold 13% more water. That's why we're getting much heavier rainfalls now, because the clouds are just holding more water. The warm air can hold more water vapor than cold air. That's just simple physics. So when you look at the tropical convection clouds, like you can see in Sri Lanka, and like when I've lived in the tropics, I've always wondered at, they're huge systems, aren't they? With very big tropical systems, with big, huge billowing clouds, like you don't see when you go to the higher latitudes. And then that graph on the right shows us with increasing temperatures, our clouds will contain more water, and we can quantify that with various increases in temperature. We can quantify the amount of water that's in the rain clouds. And then if we look at oceans, now oceans will take up most of the heat. I think it's about 2/3 of all of the heat will be taken up in the oceans eventually. And I don't know if any of you are divers or swimmers, but you will know when you go in the ocean water is 40 times more effective than water at transferring heat. That means it can hold 40 times more heat in the ocean, particularly in those certain the top 10 meters, the top 100 meters, the top 200 meters. And eventually that will be transmitted back to the atmosphere. So you'll get all these feedback loops. And that is why now the talk isn't just about the average temperature of increase. What we are realizing more and more is that our hydrometeorological systems have the ability to concentrate that heat and produce the extreme events that we can see in deep time, as I'll get around to a bit later, but we are experiencing now. So one expression of this movement of heat is the movement of water around the Earth. So the bottom diagram there shows us the various temperatures of the ocean. The top one shows us rainfall. And as we all know, the greatest rainfall occurs in the tropics. So when you get your monsoon in Sri Lanka, you all know about it because you get very serious amounts of rainfall falling in quite short periods of time. You rarely get that sort of expression in the higher latitudes. When the Earth cools, we actually compress our climate systems. So we literally take the heat out of the system, and you will not get this heavy tropical rain in the equator anymore. So when we had the ice ages on Earth, the big ice ages on Earth, the equator would still be the equator, and it would still be the warmest part of the Earth, but it would be relatively cool compared to today. And you wouldn't get these big tropical rainstorms like you get today because the heat is not in the system. And what we are doing now anthropologically is we are reversing that trend. We are putting more heat in the system. So we are pushing everything polewards. All of the climates are moving polewards. We're expanding the tropical belts. We're expanding the desert belts. We're getting hotter and temperatures and things like that, as you know. And we're also getting a focus on the heat in different places. So we've got this heat energy. And for example, if you look at the map where Australia is, and you look at that island New Guinea above, there are times on the Earth in the various El Nino and La Nina cycles where you can get an incredibly warm piece of ocean there. It's a huge piece of ocean, maybe the size of Australia within the ocean, and it can be have an average of 34 or 35 degrees C. And that is a real powerhouse for cyclones, which we'll talk about in a bit moment. Many of us live within river systems. And one of my arguments I'm going to present a little bit later is just because of the sheer number of us, we are placing ourselves in places of higher risk. When there were fewer of us, you know, our ancestors knew just as much about risk as we did, and they would live in places, they would look around them and their environment around them, and they positioned themselves in places of minimal risk. But as our numbers have increased, we haven't got the luxury of doing that anymore. And we've tended to move more into places like river floodplains or coastal areas or places near earthquake prone zones or volcanic areas, things like this, much more than we ever did before. So if we look at river systems, for example, again, we can follow the movement of water vapor into the atmosphere, the fall of the water in the river system, the whole river catchment system, and then we can define a flood when the water leaves its normal channel area, and this sort of thing. If we add heat to that system, then we are going to concentrate water more and more. We're going to get more cloud bursts. We're going to get more intense rainfall than we ever had before, and we're just going to increase the whole energy of the system and the size of the floods and the extent of the floods, things like this. And this is the new world into which we are moving into. But we can understand this by looking in the ancient record again, because, for example, if you look at this river system at the lower part of it, you can see the flat area. These are all alluvial deposits, and geologists have mapped and tried to understand alluvial deposits at all ages in geological time. And they know a lot about the extent of the biggest ever floods on Earth, for example, and we can learn about that. So cyclones are a particularly humbling sort of phenomena, which shows exactly how heat moves around and how we can drive heat from one system to another. So here from the hydrosphere to the atmosphere, into rainfall, into winds, and then back into the terrestrial environment. They tend to form, well, in fact, they do form in the tropical areas, and they either move north or south. And Sri Lanka and India and the Bay of Bengal in general is very much in the cyclone belt. Also, the geometry of the continent around it plays a part. So the Bay of Bengal, for example, once a cyclone gets into that bay, it's got nowhere to go. It's trapped, isn't it? So eventually it's going to make landfall. Similarly, we hear a lot about the Gulf of Mexico, which has got a similar sort of coastal geometry to it. And everything about these cyclones is impressive. It's got this, it's a big swirling, massive energy. And it's an example of where the Earth systems are concentrating energy, concentrating heat, concentrating winds, concentrating heat and energy altogether. And so they're producing our more extreme events. And the more we warm up the average global temperature, the more we give these more kick. So we are seeing cyclones in the last 20, 30 years, which have got, I mean, I had to manage, for example, certain cyclones, which hit Pacific Islands. The biggest one I was involved with was one called Cyclone Pam in Vanuatu. And this had maximum speeds of 320, 330 kilometers an hour. And it had such an impact on a small country like Vanuatu that 2/3 of the economy of the country was affected by one cyclone. The good news was only 19 people died, because we've learned so much about predicting these things and how to manage the actual hazard when it arrives. These are amazing. These are real tracks of cyclones. I think that there's over a certain time period. I can't remember exactly how long the time period is here, but you can see very clearly how the cyclones, they start in the equator and then they move north or they move south in this curved manner. Some of them can have a very weird path because they follow the heat. Yeah, and that's why when they hit land, they run out of steam eventually once they've expended all of their energy, because they can't pick the heat up anymore. So while they're at sea, they will actually move almost like a live creature. They will be seeking. They're like a heat seeker, and they'll move from one bit of warm ocean to the next, and they'll suck up energy. They'll suck up water vapor, and they increase in intensity. They can die in the ocean as well if the heat dies in the ocean while they're there. So what can geology also tell us about this? Well, we can go back to the records. These are pictures from the Himalayan system. So the middle one is actually Mount Everest, or Chongolungma from the Tibetan side. That stupa there in the middle is the highest religious building on earth. It's Rombok Tibetan Buddhist monastery, to the height of over 5,000 meters, and you're looking up to 8,800 meters there up the Rombok Valley. And what we can see there are evidences of, you can see the ice sheets in the distance, but in the lower ground, you can see the deposits that the ice sheets have left behind. And this tells us about the behavior of ice sheets and what And looking at ancient ones, back millions and millions of years ago and billions of years ago, it helps us tell us about the extent, the size, and the duration of ice sheets. The one to the right of there is in Tibet, and you can see big alluvial systems coming down from the highlands into the lowlands, and that's where most of the villages are. And right of that is a section through the alluvial deposits. And again, by looking at deposits like that, we can get patterns of the biggest floods, the smallest floods, the duration of the floods, the size of river systems, the size of river catchments. So we can see patterns in Earth history, and we can talk about the 1 in 100-year flood, the 1 in 1,000-year flood, and all of that. On the very left there, that is Zanskar in Ladakh, and that river has carved a very deep valley that you can see because the Himalayas are rising there, and they're increasing the energy of the river. And those little insets are some of the deposits that river produced in past times. Now we can do this with tsunamis, we can do this with storms, we can do this with volcanic deposits, we can do it with anything that leaves a deposit behind. And this is what helps, this is what tells us about the really big things. And one of the messages I'd like to get across here is that you will hear people often talking about the 1 in a 10-year flood, the 1 in a 50-year flood, the 1 in a 100-year flood. And I'm suggesting that this is outdated thinking now, that really we have to prepare for the 1 in the 10,000-year flood. We know what these things look like from geological history, and that's what we need to plan for. And we want to be more like the way we plan for seismic hazards. We cannot predict when an earthquake's going to come, not like we can if we're lucky with a rainstorm, for example, because we can track it with satellite imagery and all of that. Of course, we use the best early warning we can on top of all of this. But before we get there, we plan our infrastructure and our settlements to be resilient to the 1 in whatever we decide to do it, hopefully the 1 in, say, 1,000-year flood or something like that. No longer can we use this terminology anymore because we're just seeing records broken all the time now. And, again, we knew this stuff and our ancestors knew this stuff, and in some ways we're relearning it. So if we look at hydromet processes, we're looking again at heat transfers between the various systems. We can use heat as a tracker. We can use water as a tracker to learn about the system, to learn about the dynamism of the system, to learn about the mechanisms of the system. We know that the removal or addition of heat moves climate belts. We know about river systems from ancient deposits and from modern studies of the hydrology of river deposits. And we should now start focusing, well, what is the worst that this can do from a human perspective? Cyclones, I think, are a really good example of where the Earth systems concentrate this extra heat we're putting in the, well, any heat that's in the system, and will concentrate even more. There's that added extra hit to them. Geological deposits inform us about the past, about the 1 in 100 to the 1 in a million-year flood, and we should be learning from that. And then modern hydrology, with all of its different instruments and things, can teach us about the way these systems work today. So now getting into towards the end of the lecture, and I'm going to move to the final sort of theme, which is the Anthropocene. So the Anthropocene is very unusual for geologists. Geologists are fairly conservative when it comes to the geological column. And you probably all know about the geological column. They've got names like Jurassic and Cretaceous and Tertiary or whatever the names are. And they are developed. They're developed when we can see big changes happening on Earth. The boundaries between the various systems are when we observe changes. For example, when we see some life becoming extinct or something like that. And remember, 99% of all life on Earth has become extinct throughout geological time, but we still have life here. And this is a natural way of nature in the universe. But from about the 1990s and definitely in the 2000s, geologists and others started getting together and started saying, you know what, humans, this is different now. Humans are becoming such big planetary changes that we need a new geological epoch. They are now moving around as much material as natural processes, which is pretty unbelievable, isn't it? And then, of course, we all know about what they're doing to biodiversity, potential extinctions and things like this, and the climate. So they've come up with the idea of the Anthropocene. It's not been formally agreed, but it is there, and it's there to recognize the impact of the humans on Earth. And also the other criterion for a geological epoch is that it leaves something leaves a deposit behind. And the argument is now that we've developed such extensive cities, you know, with our mega 10 million cities and 20 million cities and things like that, plus all of the infrastructure, that some of this will survive in geological time, and therefore it will become a geological deposit in the future. And if any geologists exist in the future, they'll think, oh, maybe there was a species on it. I wonder what it was, this species on Earth. I wonder why they died out. You never know. Maybe in the future they'll look at things like that. So this is the key thing for me, is this is the growth period. This is the growth curve of human population on Earth. And I'm still astounded by this every time I look at it. If you look at the top left-hand part of this diagram, that's the 24-hour clock, which represents the whole of Earth from 4.65 billion years ago. We arrive at 1 minute to midnight. We've hardly been on Earth. We haven't even been on Earth a minute, if we think of Earth time as a 24-hour clock, and look at the impact we've had. And out of that minute, it's only the last second of that minute where we've had the big impact. So Homo sapiens arrived on Earth about 200,000 years ago, and for much of that period, there weren't many of us, 1 million maybe, or a few 100,000, maybe 10 million or something like that. Or a few thousand, something like that. And then every dot you can see on the right-hand side of that curve is a doubling of our population. And look at that straight line curve when we get to this century and the end part of last century. So we didn't even hit 1 billion until 1804. We didn't hit 2 billion until 1920, something like that. We didn't hit 3 billion until 1950 something. So from 1950 something, we've gone from 3 billion to 7 billion. Imagine if this was rats in Colombo. Who would be happy with this growth thing? If you add to that the fact that we are highly consuming as a species, no wonder we are stressing our Earth system. So geologists have said, well, let's look in a bit more detail at this curve. And they notice a couple of points. It's not just them, anthropologists, historians, environmentalists, everybody's looking at this. And there's two inflection points on the curve. One is the first industrial revolution. One is called the Great Acceleration. The Great Acceleration probably we're going to take as 1950-ish. And this is when much of the world got into the industrial revolution period of the world. And we had a mass expansion in consumerism of everything, consumerism of everything, and a big growth in the middle class. If you define the middle class as somebody who has excess money over and above what they need to survive, you know, you can go out and buy a cup of coffee, or you can have a meal out once in a while, something like that. That's what economists here define as middle class. And of course, there's an awful lot more richer than that, and unfortunately, there's an awful lot more poorer than that as well. But it's the ones that are richer in particular, and we can't talk about inequality here, but that's another thing we can look at. These are the ones that are driving the consumption more than anything and having the impact on the planet. So the base of the Anthropocene is probably going to be put at about 1950. And this is a proxy for consumerism. This is the world demand for copper. So you can see before 1860 or something, there was demand for copper, of course, but it wasn't particularly huge. Now we can't get enough of this stuff. Anything to do with the electricity, the internet, electric cars, green energy, all of this sort of stuff, it really needs copper because it's the best natural conductor of electricity, which is reasonably priced. But you can see the sheer, that's a proxy for almost anything. And we can go onto other stuff. We can look at population, we can look at GDP, we can look at tourism, we can look at urban population, paper production, the production of dams, McDonald's restaurants, whatever you want to look at, telecommunications, it's gone up the same curve exponentially since 1950. That's why it's called the Great Acceleration. So people have said, many people do this sort of analysis now. They said, well, our planet has boundaries. There are limits to our resources. There are limits to our systems. How are we faring compared to the limits of the systems? And without going into too much detail in this, well, we're not faring very well. We are exceeding our planetary boundary, probably to the level of almost 2 planets. We are using 2 planets worth of resources up at the present time, and that's impacting on the planetary systems and the hazards and the risk. This isn't new, actually. A man called James Lovelock set up the Gaia hypothesis. Gaia was a goddess, a Roman goddess of the earth. And he said that he was a meteorologist, actually. And he said, well, this was 1979, very early on for this thinking. But he was the one that said we should really be thinking very carefully what we're doing with our earth systems. This is much more recent. This is from somebody, an organization called Earth Overshoot there. And what they do is they give us a date every year at which we've used up one planet's resources. And this year was 2021. So in 2021, it was July the 29th. And here is a scale of per capita ecological footprint from the biggest one on the left, which is Qatar, because it's a big oil-rich state with not many people, to the smallest on the right, places like Afghanistan and Eritrea, which live in desperate poverty and don't really have much of a footprint on the earth. You can see Sri Lanka there. You can see a whole range of countries just to see where you are on the list if you want to have a look at that. The blue means anything to do with carbon producers and consumers. So you can see everything to the left of that diagram. It's largely the carbon footprint. And then the others are impacts on grazing land, so that's farming and forest farming and agriculture, impacts on fishing, the growth of urbanization, and then the growth in crops. So you see when we get to the right-hand side, it's largely in the agricultural space where we're having the impact. And then we have the tragic story of the 6th extinction, probably as bad as any extinction we can see in the geological record. And there's this lady, Elizabeth Colbert, she says Homo sapiens might have enjoyed brilliant success in one area, but it's at the expense of every other species, probably even ourselves as well. And you can see by various indicators, this is WWF, we're impacting on 68% of the Earth's species to the negative. So what do we learn from this? I think from the Anthropocene, for me, the root cause is us, is humans, whichever way we dress it up. I think we'll fix carbon, actually. I think we'll fix greenhouse gases, but we're not going to, then there'll be another issue beyond that. We are always going to impact on the systems. So what are we going to do about us? We're also so many now that we're moving into areas. You look at where the cities are located. They're nearly all located next to the seawater, like Colombo, like where I am in Auckland. So many cities are next to sea level, or are not much above sea level, and sea level will be rising, and the climate will be such that the ocean weather will be picking up in terms of its aggression, and it will be impacting on the coastal zone more and more. Humans in recent times have not respected planetary systems like we did in times gone by. So what can we learn from all of this? One of the key impacts of humans is in the increase in disasters, meteorological disasters. Of course, we can't, thankfully, increase earthquakes and volcanoes. So they stay the same, but they still have an impact. They impact more because of our greater numbers. So, with any particular, if you look at Haiti, for example, which has just had a terrible earthquake and had one 10 years ago, 20,000 people died in the recent one just a few months ago. I think it was 20,000 or more died in, 2,000 died recently, 20,000 10 years ago, something like that. And it's wrecked the economy of the poorest country in the Western Hemisphere. So all of these diagrams here are telling us that pretty much, if you look at that central one above the arrow, all of the data are telling us what that arrow is doing. Everything's going up. There's some good news is that we're managing to manage deaths. So deaths are going down, actually. So we're managing that all right. Unfortunately, most of the deaths are in the less developed world, or the low-income countries. The least deaths are in the countries that can afford to put in a lot of expensive infrastructure development. But then on the other hand, the greatest expense to the economy is in the Western economies, because they've got more to lose, haven't they? So there's swings and roundabouts, I guess, on that. So here we're looking, for example, on the left there, well, in fact, in all of these, it's number of recorded disasters. One is just simply all disasters added together. The bottom right are different styles of disasters. And then we're looking at temperature. We're starting to get temperature above 50 degrees C in different parts of the Earth. The diagram, the BBC have just brought this out, actually just yesterday. In fact, they brought these curves out. The one on the top right there shows how the amount of 50 degrees C days is increasing in different parts of the Earth. Well, that's exceptional, but let's just take it down to over 35. You know, Colombo, you're getting that now, aren't you? Over 35, things like that you didn't get before. And of course, this stresses the situation. So what can we learn from this? That's a beautiful picture. I've been working in Ladakh in Northwest India. Pre-COVID, I was out there for a couple of quite long seasons, looking at those complicated structures you see beyond. And that's a Tibetan Gompa, or Buddhist monastery. In the foreground, a place called Tikse, which is, they have these very beautiful Tibetan style, it's Tibetan culture in this part of India. And actually you can see in the lowland is the Indus is in the valley, just below the Gompa, and the going down to the river, you can see these big extensive alluvial systems from the mountains. Well, what can we do about this? For me, the number one thing is population. Very controversial. I'm quite saddened because there is not an intelligent debate about linking climate change and population. Nobody seems to want to pick that one up and run with it, because I guess it's controversial. People don't like to talk about it, but I think one day we're going to have to talk about it. And a lot of people have been doing modeling, and they suggest that really, if we want to live like we live now, then probably the planet can't cope with any more than 3 billion people. And of course, we're getting up to 8 billion people now. Now, I'm not condoning mass genocide or anything like that, but I think starting to manage the population and not delaying this anymore is something we should be doing. What about more locally? What are the lessons from all of this for somewhere like Sri Lanka, for example? Well, luckily for you, you're not in a tectonic area, but unluckily for you, you are inside of an ocean which is very active tectonically, and as you saw from 2004, you can get devastating tsunamis. Now, that's not the first tsunami that Sri Lanka ever had. It's just we forget when these things happened before. Probably if you look back in time in the historical record, you will see records of older tsunamis. And certainly if you start looking at the geological deposits, you'll find tsunami deposits. Similarly, landslides will be going up with the increased rainfall. You will not get seismically induced landslides, but you'll be getting more rain-induced landslides. You'll be getting changing and more intense monsoons. As you know, you'll be getting increased cloudbursts or intense rainfall, which will lead to increased flooding. You'll also be getting drier periods and droughts and maybe larger dry zones and increasing droughts in the northern part of Sri Lanka. Sea levels are going to rise. This may or may not be an issue for you. It might be for some communities, for others, not so much. And you might be seeing more aggressive climate in the coastal zones, and you'll be getting higher maximum temperatures, which I know anecdotally I've heard from people that people are struggling from, but I think we need to scientifically look at this and not just rely on anecdotal commentary. So what can we do for this? I think mapping, monitoring, measuring, and moving data into preparedness and policy is one thing that Sri Lanka, all countries really, but Sri Lanka could focus on a bit more. For the urban areas, the biggest one being Colombo, but for other urban areas too, Colombo has become much more of a concrete jungle than it was before, which is a mistake, isn't it? You really need to think about how you urbanize with the environment in mind. And, you know, as we know that there's a very local effect between big cities and the local climate and the environment. And you can make matters worse for yourselves, or you can make matters better for yourselves. I went to a very good conference a few years ago where Helsinki, for example, and of course, it's often these Nordic countries, they've got plenty of money and time and they can think about these things, but they're doing all sorts of wonderful things. So is Denmark and places like that to try and mitigate and, if you like, control a little bit the very localized environment. And then one great thing is, we're talking about reducing the population to 3 billion. Now that's going to take time, of course. But the other big sort of wild idea is wilding the planet, isn't it? We're only going to get biodiversity back again if we get out of areas and just leave places to nature. And the big suggestion is we get out of half of the planet for that. And the good thing about Sri Lanka is you've always had these sanctuaries, yeah, and let's hope you always can keep them, and that really helps preserve the wildlife, the biodiversity, and the climate. For a place like I'm speaking to you from, Aotearoa, which is another our indigenous name for New Zealand is Aotearoa. For here, we're looking at a different type of country socioeconomically, and we're looking at a different climatic environment. So we're not going to worry so much about hotter temperatures, although in Auckland, we can get quite hot temperatures now, up to 30 degrees plus in the summer, and this does stress the environment and the people because they're not so used to it. But other parts of New Zealand, perhaps less so. Unlike Sri Lanka, though, we are in a geophysical area, so we need to take note of earthquakes, volcanic eruptions, landslides, things like that, both seismic and rain-induced here. And although tsunamis have not been an issue in human history here, but the human history here is fairly short compared to Sri Lanka, theoretically, this is a place where we can get tsunamis. Luckily, we've just had the deployment of early warning buoys as part of the Pacific system for tsunamis. And there's a lot of work going into looking at ancient deposits. Luckily, also, New Zealand funds a number of institutes which monitor things like earthquakes very scientifically and very comprehensively. So it's lucky from that point of view. Let's hope it will keep the investment up in that area. On the hydromet side, there's going to be a lot more flooding here. They're talking about that. They're talking about parts of North Island becoming much drier. That's going to affect the agriculture, particularly avocados, for example, and things like that, which rely on a lot of water, I understand, to grow them. There will be sea level rise. The lucky thing with New Zealand is it's tectonically very active. So actually, it can actually rise even a few meters in one earthquake, different parts of it. So only parts of New Zealand are going to have to worry about sea level rise, but Auckland, where I'm speaking to you from, will be one of those. And there's increasing wildfires here, which haven't really been seen before. So there's a bit more of a focus on that. So what would be the activities for somewhere like New Zealand? Again, map, monitor, measure, just like Sri Lanka. The urban areas, I feel New Zealand personally, I feel is a little bit slow in compared to other OECD countries in terms of moving its urban environments into greener spaces and things like this. However, for the rural environments, it's actually doing incredibly well. Apart from the fact it's intensively farmed for the very small population, only 5 million people here, but such a huge amount of areas is farmed intensively and scientifically with lots of chemicals and stuff. So wilding the country is an aim of many people. So last slide, I've been through most of this, but just to summarize the lecture, detailed scientific analysis of Earth systems and all that entails. Learning again from deep time and geology and all of its different ways. Moving away from this 1 in 10 year or 1 in 100 year flood to expecting extreme events to happen much more regularly and adapting to that. I would call that a seismic model approach, for example. Thinking much more smartly about our settlement. We've actually started to develop so many areas. We even move into places that we call floodplains, and they're called floodplains for a reason. And I know in parts of Colombo, you have that issue where, that they used to have wetlands and you used to have floodplains. You don't have them anymore in the way you used to have. And that's going to come back to bite you and when the big events, the big risks arise. Prioritize the risks. listen to the Anthropocene. And I think, you know, there's a lot of talk in the media, for example, about countries which have a lot of older people, like Japan. They always talk about Japan, and also they talk about Japan and the fact that it's flattened out in terms of economic growth and stuff. I would like to turn that on its head and say, well, Japan isn't a bad model. It's actually got its population in control. The older people have a very good quality of life compared to past times, and look, they live very comfortably. Why do they need to grow their economy anymore? Can you really grow an economy forever? Personally, I don't think you can, and I think it's the wrong way of looking at the world. All right, I'll stop there, and thank you very much for listening, and hope I haven't gone on too long, and I'll be here for any questions.
Thank you very much for that interesting talk, Professor Petterson. I myself have learned a lot of new things, and I think now we can move to the question and answer session. So to start with, I would like to ask 2 questions actually. So Sri Lanka has got a tsunami in 2004 after 1907. So does this Wilson cycle play a role in having not having anything in between this period? I'm sorry if I have missed anything.
No. Could you repeat? You said Sri Lanka has a you said tsunami 2004. And then what did you say before?
We have had it in 1907. So for quite some time we didn't have anything in between. What was the reason? What could be the reason for that?
Okay, so your Sri Lankan tsunamis, as you know, originate elsewhere. Yeah. So if we look at the 2004 tsunami, that was a very big earthquake. That was a magnitude 8+ earthquake, and it was over a considerable part of the fault, and the fault moved to produce considerable topography on the ocean floor, which then pushed the big ocean wave, you know, around Sri Lanka and elsewhere. The good news is, once you get up to those size of earthquakes, they are not particularly common. Yeah, so you might expect to get 1 or 2 or 3 or 4 of those globally in a century, every 100 years. That will explain why you have time gaps between the different types of tsunami. So you might be lucky and you might not get a big tsunami like that for a long, long time. But actually, we know the fault system that produced that tsunami. There's been a lot of studying in that fault system. And we know that another part of it, opposite a town called Padang in Sumatra, that part of the fault is now looking very stressed. If it releases all that stress in one go, then there could be another one. So when that is, of course, that's a problem, is we can't predict. We can't predict the when, but it's not looking good. And Padang is gearing up, you know, it gets its tsunami in 10 minutes. It gets no warning at all. So it's got to manage that risk more in a different way to Sri Lanka. The good thing about Sri Lanka is you will always get about 3 hours warning, because most of the faults that produce your tsunamis are that far away in terms of travel time. And the other good thing is, the bad thing was, you know, you had so many casualties and all of that. But hopefully, you know, people have learned from this and learned about escaping, learned about forewarning, learned about how they build the houses, the settlements, look for the signs of the, you know, when, for example, the reef can go dry as the wave approaches. And at least in living memory, people will take a lot of notice. The problem we have as humans is we forget. And people who work in risk know that after about one generation, you know, people say, oh, that was a long time ago. Why should we worry? And if you talk about it, they talk about you as the angel of death. You know, we don't, you're always telling us about all these bad things. We don't want to talk about that. And yeah, so in terms of I can't answer your question in terms of the interval. The lucky thing is that big earthquakes are not that common. So it could be a long time. But then again, it could be tomorrow. And that's the problem. That's the problem we have.
Yes,
Yeah.
thank you, sir. The
Yes,
next
thank you
question-
very much, Mike. Actually, just wanted to thank you, extend my sincere thanks on behalf of the department and on behalf of the Ministry of Nerds for the very insightful, interesting lecture. To add more to what Sachini said and your explanation, the last week and the previous week, some parts of Sri Lanka, especially the southern coast, they experienced a few tremors. And there have been very minor earthquakes in the ocean.
Oh, okay.
Thank you, madam.
And there are some questions in the chat box, Mike.
Yes.
Oh, all right. Let me look in the chat box.
Can I read it to you, sir?
I can see it now, actually. Let's see. So the second one is from Mayuri. Thank you, Mayuri. Given the natural phenomena have played significant role in determining condition species, blah, 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 to what degree could humans intervene to prevent the inevitable? Well, my answer to that would be there's two things. There's things we have control over and there's things we don't have control over. So also we have to let natural systems do their thing. Yeah. And for example, we probably would love to still have woolly mammoths around so we could go and look at them and watch them and, you know, have them as pets or whatever. But, you know, it just happened that the conditions that created them are no longer around. And that's just nature, and that's just life. I don't think we should be worried so much about that. That's just the way where things happen. Where we should worry is where we have control over things, and where we realize that our actions are having reactions, negative reactions. Which is what all this climate change debate is about, and similar debates. That's when we can decide what we can do. But the problem also is we have to get big agreements all across the world. When have humans ever agreed globally on anything? So it's that one's a big challenge. So I would like to know whether global warming has any effect on the continent movement in the Wilson cycle. Probably not much. There are some impacts between global warming and some geological processes. I'll give you one example. One of the reasons volcanoes erupt is because the pressure of the magma under the volcano is higher than the pressure outside, and then it erupts. So quite a few volcanoes on Earth are under ice, and the weight of the ice stops some of the eruptions. As the ice is thinning, actually they're erupting more, we're noticing. So there's one example where there's an interaction between a surface process and a deeper process. In terms of the great tectonic systems, so that's internal heat, which is the biggest control there. Thank you very much. That was from Lahini and Wihanga. Thank you very much. Thank you for listening. During the past, most of the human civilizations were developed in river valleys, yes. According to my idea, what could the driving forces which caused the ancestors through the flood risks and all of that? You're right. Many moved there, and that happened when we developed agriculture. So that was about 10,000 years ago. Before that, most humans were hunter-gatherers, and they would move around, wouldn't they, a lot more, and not be so set on one area. But from the agricultural revolution of 10,000 years ago, they went where the soils were good. And of course, the soils are particularly good in floodplains because, let's take the Ganges as an example. Why does something like 600 million people live in North India? It's because, historically and today, the incredible Ganges and the Indus have produced floodplains that can produce this very fertile soil. Similarly, Bangladesh. You know, when Bangladesh is, as Dimitri's looking at the moment, when Bangladesh floods, sometimes 2/3 of them, 2/3 of the country is beneath water. The big difference 10,000 years ago, we're only talking about a few tens of thousands of people in the whole Earth. So they had plenty room within the floodplain, for example, to build their houses in the higher areas. If you look at indigenous people today, they tend, I'm generalizing, of course, but compared to urban dwellers like many of us are, they tend to be much more aware of their natural environment and to live with the environment rather than try to control it. So if you look at, ancient cities, I'll give you an example from, I'm from England, and if you go to some old cities in old villages in England, the church where everybody would put money in to build the church, that was the most valuable thing in the village. That was always built on the highest ground above the floodplain. And when floods happen today, these ancient churches often are above the floods, whereas other houses, more recent ones we've built, are affected by the flooding. So it just shows you that, and that was 1,000 or hundreds of years ago, rather than thousands and thousands of years ago. But it just shows there was a sort of a wisdom that maybe because when you develop a housing site, who makes money? People make money out of it, don't they? And that's the big driver for that. So thank you for that question. Next one, Irandati. Thank you, Irandati, for your question. Thank you for your question. Thanks for showing the temperature curve. Could you please tell us what kind of geological fossil data have been used in creating it? Currently use ice core data, Yeah, thank you for that. So there's a few proxies we can use, and it's a similar thing to what you're saying. So what are you? Yeah. The great thing about ice, as you're saying here, is it stores the atmosphere, and so from that we can get very direct measurements. I think actually we can go back 700,000 years now in Antarctica, is the oldest one. Before then, what we look at actually is we look at a whole bunch of things, but we look at carbon and oxygen isotopes. We look at the isotope systems, and one of the things that people look at are deep sea sediments. They look at carbonates in caves. They look at carbonates. These are limestones and things like that. Deep sea carbonates in the oceans, and other things. And these are proxies for temperature. Of course, we cannot. It's not like a thermometer in your mouth. We can't record the actual temperature in terms of a direct recording. So we have to use lots of arguments for the different temperatures. But there's a whole bunch of information comes together, and then you can set up for different geological periods. We set up paleoclimate maps because we know what the biodiversity of the time was, and we know what the ecological limits of the different species were. What and probably probabilistically the sorts of environments they lived in, whether it was submarine, terrestrial, in a forest, on flat land, what sort of temperatures it would have been, and these sorts of things. So we have a whole bunch of information we can use to give us proxies for temperature going back in time. But it's not perfect by any means. It's a model. Yeah.
That's why actually what you showed it looks like a perfect curve. So I was wondering, that's why I asked. Thank you very much.
Oh yeah, but also as you notice that if you look at curves, for example, if we look at modern data, they're only going back to about 1870. Yeah. And because we're measuring temperatures almost every second, aren't we? We can plot very jaggedy curves. The further back in time you go, you don't have that level, that luxury of the very regular temperature measurements. So yeah, it's a lot more smoothed out. In reality, it would be jagged, like modern curves.
Thank you.
Thank you.
We get questions. I have another question, sir. Now, when you take Japan, usually Japan faces a lot of natural disasters like tsunami and earthquakes and all that. But South Korea being very closer to Japan, they get very less disasters. So in addition to the fact that Japan is a set of islands and South Korea is not, what could be the other reasons for lowering the risk?
Yeah, very good question. Thank you for that. It's all to do with the tectonic situation, the local tectonic situation. So Japan is above like a subduction zone, right, all the way down. and it's a very active subduction zone. So these plates, it's actually right on a plate boundary. So all the countries that are on plate boundaries, and New Zealand is another one where I'm speaking to you from. You know, we get many earthquakes and volcanic eruptions and things like that. So Korea is in a different position. It's that much further away from a plate boundary that it's got less of these issues. However, it does have some quite young volcanoes and volcanic systems. So it's not completely out of the active tectonic area, but it's enough away from it that it doesn't experience the very high frequency and the high intensity hazards that Japan does.
Thank you, sir.
Many are having a question, which is not an academic question actually.
Yes.
How does Mike speak so good so good Sinhala?
Oh.
No, I speak very poor Sinhala, but I have a Sri Lankan partner, so I'm trying to learn your language.
Oh, that's great.
But I'm not doing it very successfully. I keep getting told off most weeks for being lazy at learning, but I'm trying. I'm a lot better than I used to be, but I'm not there yet by any means.
Thank you for your love for Sri Lanka.
Okay, then let me officially thank Professor Petterson for joining with us today, for taking your precious time to share this incredibly informative and interesting information with us. And I would also like to thank Professor Deepthi Wickramasinghe, the Principal Investigator of the Environment and Resilience Bit, and her team members for hosting today's seminar. And thank you very much, everyone, all academic, non-academic, staff members, students, and all the participants for joining with us today. We hope to see you in our future events as well. Stay safe and have a good day.
Okay, thank you, everybody. Thank you for listening, and thank you for coming. Bohome City and Budu Saranai.